Recording is rolling. It is Tuesday, October 29th. There was a page I gave you guys yesterday. It looks like this. I have a correction to make on that Greek table. We'll look at that pretty soon. The main focus today is going to be chapter 7 puzzles. I want to go over these, show you guys how to think about them, point to the solutions. But uh, if there's some class time, I'd really like to give you guys some time to work independently, and I can walk around and troubleshoot any questions you guys have individually. All right, guys, AP Classroom. I know that was we went over the first half of that yesterday. You guys can still submit it and still put in points. Oh, here's something I forgot from last year is that there's always like a handful of students that want to just Christmas tree this thing. Guys, if I see you're getting fewer than 25% of the questions right, which is like worse than a proverbial monkey, just like HCP, then yeah, no full credit for you. So yeah, so I mean, got you at least 25% right. You're trying to also reasonable time because I can see how much time you're spending on each question. So if it's like 3 seconds all the way down, then I know you're just clicking it to get done. No, I mean if you miss some questions, it's not going to hurt your grade. But I want to see like you at least putting a sincere effort towards that. All right, if we get some extra time in class, I do have more demos for you guys that I want to do, but we'll see what we have time for. All right, let's look at this page. You guys see commonly used Greek variables, well, I guess Greek letters, so letters from the Greek alphabet. Most of these are variables, some of these are constants. All right, I made a typo. It looks like it's fourth from the bottom. See the one that looks like, here, it looks like this. You guys see one that looks like this? It should be capital rho. I put capital sigma, but it's not sigma. So guys, strike out sigma. You guys see where it says capital sigma? That's not a sigma, that's a rho. RHO, capital rho. Okay? All right, so here's here, I wrote right here. So it's a little bit bigger. All right, so this symbol is capital rho. That's used to represent ohms, which is a unit of resistance. I'll go over electricity and circuits with you guys very briefly next semester. This is not going to be on your AP exam, but I think it's good to know how to do circuits. So like how much resistance could be in a resistor and a light bulb and a wire. You can quantify that in ohms, and this is the symbol for that. Right. There's also a lowercase rho, which is on here. Now this one's correct on your paper. Right. Stands for actually a couple uses. Density. You guys have seen this class, like actually some recent posters, like what's the density of the planet? Like mass per unit volume can be used for that. Also for electricity, there's a use for resistivity, which is like a material property. It's related to resistance, right? But it's like a material type property. Right. Now there is a capital segment. Actually, I should have put on this table. So I went back and here, I'm gonna amend this a little bit. So the capital segment, that's this one here. That's this like jaggedy E looking character. And guys, what does that mean? Yeah, summation. Yeah, it's like you're adding up blah 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 blah. You guys saw it. Actually, do I have it right here? Hold on. No, I don't. Okay. You guys remember that center of mass I was showing you guys? Right, the sum of mass times location divided by the sum of mass, right? Or sometimes you use for net force if you sum all the forces together. All right, you guys know that one. All right, the lowercase sigma looks like this. Oh, so in engineering, I know that's used for stress. In statistics, I knew it's used for standard deviation. You guys might see it a little bit. We possibly talk about quantum, maybe near the end of the year. I think it's also one of the physical constants I think is commonly used, sigma. All right, so there you go. There's a little bit better Greek amendments there. All right, any questions so far before we start looking at these puzzles? Guys, right so far. All right. So look at these puzzles here. Here, the ones I'm assigning that I'm gonna see that you guys said are just the circled ones. Like always, if you want some extra practice, there's some that I didn't circle that are really great questions too. And the solutions are also, of course, posted. Right, so you guys got this. Let's check them out. The first one, number 5, dentist drill starts from rest. After so much time, it's going so many, hey, revolutions per minute. Right, and then they ask a bunch of questions about it. That really, to me, sounds kinematic. You guys think that sounds kinematic? Right. And do you guys think also you probably want to convert from revolutions per minute to radians per second? That would make sense too, right? Okay. Show you guys exactly where to find this. So on your AP Classroom, right, I mean, you guys probably found this already, but right, so week 9 through 12, that's where we are here. We're on week 12 of school, by the way. You scroll all the way down to the beginning. I posted a bunch of files, including, hey, college physics solutions right there for chapter 7. Right, so that looks like, right, if I open that up, I got it right here. All right, oops, start at the top. All right, and so, yeah, look, I start off a unit conversion to convert from revolution per minute to radians per second. Right? And then, hey, this is rotational kinematic. So look at what you're given. It starts from rest. You might have to figure out omega naught equal to 0 radians per second, right? And then what can you solve for using kinematic equations? All right, that looks pretty good, right? So we got that. All right, see what's next here. So leave that to you guys. Number 15, a car turning around a circle. Hey, and they tell you how far it goes and how much time. Ooh, do you think you could calculate its speed? Notice I'm not saying velocity, I'm saying speed because it's going around a curve. And then once you figure that out, what's the magnitude and direction of the acceleration of the car? That sounds kind of like this centripetal acceleration for a magnitude anyway. Right? You guys, here, go ahead and tell me right now. Going around a curve, what is the direction of that centripetal acceleration always? Towards the center of the circle, towards the center of the circle. That was another poster that I don't have in hand, but you guys get that. All right, what else we got? It's been suggested. Number 16 is talking about O'Neill cylinders. O'Neill cylinders. They're talking about this right here. So you give this a spin. You could ask any number of questions about this. Here, guys, suppose you want, you know how large it is. You want to calculate which of the gravity field, or here. What if you target a gravity field of 9.8 meters per second squared? See all these people walking around the inside? Okay, so you have a target acceleration type value. You know the radial size. Can you calculate how fast to spin it? If you do that, right? Or I guess if you know any two of these variables, you could solve for the third kind of thing, right? Something like that. O'Neill cylinder, I guess you do that. Yeah, some more stuff I could say about that, but let's move on here. Adventurous archaeologist swinging on a vine. The vine can handle so much tension before it snaps. Actually, well, what is it? Number 18. Let's go back over these solutions. Let's see. Of course, I got all the solutions here, but we scroll down. See if I find number 18 here. 16, O'Neill cylinder, 18. I think the first thing you should do is the first thing I did is make a free body diagram. Guys, he's swinging on the vine. Swing. Guys, at the very bottom, free body diagram. He's in motion. He's in motion. Which force is bigger, his weight down or the tension force up? Tension force up. It sure is. There is a net force on the sky. Here, take the difference. There's a net force, which is the centripetal force mv squared over r. You guys see that? See how it all kind of clicks together? Right? And then any number of questions you could ask about that, but that's the setup. Okay, there's that. Now, this setup, hold on to this idea, because in a few weeks we're going to do conservation of energy. This puzzle's going to come back, and we're going to get an extension on this. You guys see this initial angle right here? Suppose I give you this initial angle is like, 43 degrees, or whatever angle from the vertical. You see that? Do you think you could, in principle, calculate, hey, if I start from rest, how fast am I going to be going down at the bottom? Right? You could do that, right? Now, at this moment in the class, they're giving you that. They're saying, he's going 8 meters per second at the bottom. But in a few weeks, you'll be able to calculate how fast based on, say, this initial angle, and also how long is the pendulum. You'd have to know that too, right? It's a pendulum type question with the swinging on a vine. All right, so we got that. All right. All right, see what else. Number 20. Ooh, a coin on a turntable. Guys, a coin on a turntable. That sure makes me think of this, which is a lab I still want to do with you guys. We're either going to do this later this week, or I'll use it for a review lab in the future if I don't fit it in this week. Okay. But the way I set up this poster is to solve for the coefficient of friction based on, well, if you know how fast you're spinning it when the coin slips off, maybe something like that. Okay. I think they asked a little bit different order. I think they gave you the coefficient of friction, and I think they have this accelerating, so they gave you an angular acceleration. And they want to know at what time does it slip off. So it is this in a little bit different order because they gave you the coefficient of friction, so not exactly what I have target there. But also, where's my? Didn't I just have the kinematic equations up here? Okay, combine it with the kinematic equations. You guys can do that, right? Kinematic equations, right? Because here we go. Right, because if they gave you an angular acceleration after some time, then maybe you could say like how fast is it spinning, which would correspond to like the like breaking the friction off, right? Something like that. All right. You know what's going to be helpful is maybe something to do with like these down here, right? So how fast is it rotating, radians per second, or something. All right. So there's a bunch of puzzle pieces lying around. See if you guys can put those together. All right, number 32. Hey, look at this roller coaster. It's going through a valley and then over a hill. Okay, through a valley and then over a hill. I think I got that here. That's like, here's a hill and a valley. All right, so just reverse order. Right? I might draw some free body diagram. There's a free body diagram. There's a free body diagram. Guys, notice there's a net force on the car at each location. There's a net force, right? It's overall down on the hill. It's overall up on the valley. You see that, right? And do you guys remember this one? Now we use this a few stories. There's water in the cup. Say like, what's the minimum speed to spin around, make sure the water stays in the cup upside down. Same thing, roller coaster going through a vertical loop. But hey, what if you applied this to going over a hill? Guys, if you drove too fast over a hill, do you think like fly off like Dukes of Hazzard? You guys think? Yeah, probably so. I bet that can also be answered by this. Just think about a little bit different context. I bet it's really similar though. But you guys can figure that out. All right, number 37. Objects with such and such masses at such and such locations. And there's a couple of questions about gravitational force. That sounds like this universal gravitation. Do you think you could maybe set some objects like this? I think you guys had an AP classroom question we went over. Like if I throw a third object in the middle, let's say, well, it's being pulled to the left and pulled to the right. Like where could it zero out? Maybe something like that. All right, I think it's one of the questions they asked there. All right, what else we got? 43. A satellite of Mars called Phoebus, so one of Mars's moons, has an orbital radius of blah 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 and a time period of blah blah blah. All right, what is the mass of Mars? Guys, that is talking about this orbital speed. You guys see this poster right here? This you need to be able to derive from scratch. When we're reviewing next semester, and there's like, here we got like 2 weeks until the AP exam in May, whatever. Right? Then I'm telling you, one of the review questions is going to be this. I'll say, pull out a blank piece of paper and derive orbital speed from scratch. And this is exactly what I want you to do. I want you to say that, all right, well, something's in orbit. We're talking about there must be a centripetal force at play, and it's provided by, well, the gravitational force, because that's the only force acting on it, right? The only force on that moon, it's just the planet Mars, right? From the Mars moon system, right? Right, so, okay, and that leads to this. Here's centripetal force, here's gravitational force, and then you can solve for the orbital speed. Here's that. Right. Now, this particular text question, they actually want you to solve for the mass of the planet. If you can kind of know what is the orbiting speed. Is it? Because it goes around so far in so much time, right? So you can calculate the speed from distance over time, just like you did on your Plato canister lab, right? And then you can calculate what's the mass that's being orbited. You can just do a little algebra. You guys see that? Right, that's what they want you to do there. All right. 44, a 600 kilogram satellite, which you guys know the mass of the satellite probably has nothing to do with how fast it has to go or anything like that. And circular orbit around Earth at a height equal to Earth's radius. Ooh, right. Calculate the speed, the time period, the gravitational force acting on it. Okay, so yeah, I bet this could be helpful right here. Okay, for that one also. Okay, a couple more. Number 56, show that escape speed is directly proportional to the radius of the planet. So guys, if you make a planet bigger, so bigger radially, it's also getting more massive also, right? Is that true? Right. So, right. Here's, supposedly what they're saying here is if a planet is like 3 times the radius of Earth, it would require 3 times the escape speed. That's the claim they're making. All right, so I'm going to give this to, say you're allowed to know this. I'll tell you guys what, AP is not going to ask an escape speed question, but they could ask a proportional question. In fact, they're going to ask you guys proportional questions. So you have to have the skill anyway. So you're allowed to have this. Okay, so write this down. I'll prove this to you guys in a few weeks, right? Where this actually comes from. Right. Right, so start with this. And supposedly, the larger radius of the planet, you need a faster escape speed. Guys, as radius increases, doesn't the mass also increase? Actually, let me go ahead and find exactly the solution on this one, number 56. And I'll just point it out on the pre-written solutions just to save us a little time here. Right. Right, what exactly you're supposed to do with this? What? No, couldn't load. Okay. How far did that get? Number 20? You know what?
Try reloading the page.
All right, refresh the page. Yeah, let's see if this works. All right, if this doesn't work, I'll just write it out on paper. I can work. There we go. All right, trying to find 56, I think, right? Yeah. Oh, good call on that refresh. All right. Oh, hey, look, there's, I think that's Mars there, something like that. Where's, all right, 45, 47, 48, 50, 55, and 56. All right, so here's your escape speed. So you're allowed to have that. All right, now, guys, here's a trick. Because as the planet gets more and more radial size, gets bigger, in terms of its physical size, it's also getting more mass. Right? And that's here, guys. If a planet has like 3 times the diameter and it's the same density, then how many times the mass is that? 3 times 3 times 3 is 27. 27 times. You guys remember scaling from way back in the day? It's one of your thumbnail notes, scaling poster. So as you scale up a planet, radial size, yeah, it gets bigger radius. It has like square times the area and a cube times the volume and therefore the mass. Right? So you guys see this expression? Volume of a sphere could be 4/3 pi r cubed. You guys remember that? Okay. Now, the important part is volume is proportional to r cubed. If you didn't know the 4/3 pi, that just turns a cube into a sphere, then that part cancels out anyway. Right? But the proportional to r cubed matters. You guys see I substituted right here? So here's escape speed, but instead of mass, look, I did density times volume, and for volume, I put 4/3 pi r cubed. You guys see that? Here, I guess I'm just giving you guys the answer right here. But see if you can pull out a blank piece of paper and do this all from scratch later anyway. Because this is one of those type puzzles that you're gonna have to have the skill. I have r cubed on the top. I have r on the bottom. Hey, does one of the r's cancel? Leaves you r squared. That gets you down that step. And that r squared is inside a square root. So you can pull it out and just say, it's this whole square root all times r. You see that? Oh, and there it is. So the escape speed, therefore, is just plain proportional to r. That's it. Right. Everything in that root, if you notice, is all constants. 8/3, that's a constant. Pi is a constant. Gravity, that's universal gravity constant. That's a constant. This is 6.67 number. Rho could be the density of the planet. We're assuming that's a constant too. Okay, so there you go. So, all right, and I think there's one last one here. Let me find it here. It's that amusement park ride number 75. They got this amusement park ride. Find this 75. All right, I would start off by drawing a free body diagram. So that guy's in the spinning centrifuge type ride. He's against a wall, but he's not falling off. Why is he not falling off? His weight's pulling down. His what force is pushing horizontal? Sure, it's acting as a centripetal force, but you're not going to label it centripetal force. You're going to label it a normal force from the wall, right? Normal force, right? And hey, what's this vertical force that's actually preventing him from slipping down? Like a friction force. Right? Actually, you guys did see an AP classroom question like that. You guys were like pushing a block against the wall, right? And that was the answer, was the weight had to be balanced out by the friction force. Right? You guys saw it yesterday, right? Right, so here, did a little equation, set up, and then I could, what did I solve for? Oh, the minimum coefficient of friction. Right. So the minimum coefficient of friction would be about 13%. You think of it that way, right? So this friction force has to be at least 13% of the this normal force. Looks like my diagram is definitely not to scale. Okay, but you guys get the idea. Okay. All right. So that could be the answer. All right, and then yeah, lots of other ones if you want a little extra practice. All right. Did I have a poster for that too? Maybe like be kind of like this one again, right? For the amusement park, right? Think of it kind of like that. All right. All right, that's all those there. Here, let's do some of these extra animations. Whatever. Right. So one thing I wanted to tell you guys about, this is a little bit bonus content, but it's fun to learn about, right? When you're at school. How about Lagrange points? So here could be the Earth orbiting the sun. You guys see that, Earth orbiting the sun. Do you guys think there might be a point between the Earth and the sun where the sun pulls you to the left, the Earth pulls you to the right, and it cancels out? Right, the gravity field cancels, like it's a wash, right? And that point, guys, would that point be closer to the sun or closer to the Earth? Closer to the Earth, yeah, right? Because because the sun's more massive, more gravity pull. So yeah, so closer to the Earth, so where it could cancel out. Okay. Now, if you also consider orbital mechanics, here's the Earth going around the sun. Do you think there could be a point I have labeled L2 where they're both the sun and the Earth pulling you to the left, but maybe you could be kind of along for the ride, so you see the Earth beneath your feet, but you never actually get any closer to it going along around, right? That's the L2 point, right? Do you guys hear of a telescope called the James Webb Space Telescope? Right, that's actually orbiting this L2 point, right? And the advantage it has, because it's way out in space, it doesn't really get blocked by the Earth. Like the Hubble telescope is orbiting the Earth, so half the time the Earth is in the way of whatever it's trying to take a picture of, right? But James Webb is like way out here. It's just orbiting this L2 point. Right. Well, if there's an L2, you think it kind of makes sense. There's probably an L3 over here on the opposite side. So you can kind of be along for the ride going this way, something like that. Right. Right. And then a guy named Lagrange did a bunch of fancy math. He came up with, he said, you know what, I think if you draw an equilateral triangle right here, and this one's also an equilateral triangle, that at these points, there should be sort of a point of gravitational stability. And that was actually backed up by observations of, well, here, I'm going to find this. All right, I've got this demo. I just pull up here. Here it is. All right, whoop, come on over here. Here we go. All right, so what do we look at here? Animation. Hey, here's our solar system. There's the sun in the middle. Here's the inner planets, Mercury, Venus, Earth, Mars. Okay. Hey, what's this one going around right here? Jupiter. Okay. Guys, the biggest mass in our solar system by far is the sun. It's like 99 point something percent of the mass of our solar system. What's the biggest mass after the sun? Jupiter. So between those two, the sun and Jupiter, that drives a lot of the orbital mechanics of our solar system. Right? What's all these little pink dots here? What's those? Asteroids. That's the asteroid belt. Well, it looks kind of triangular, doesn't it? Because here's L4, here's L5, and here's L3 from Jupiter to the sun. L3 is over here. Hey, looks like that, doesn't it? Right. And how about those green patches? Those are also asteroids. Those are called Trojans and Greek asteroids. So those are asteroids that are kind of trapped in the L4 and L5 points from Jupiter to the sun. Let's got those two. Right. Right. What else do I have for you guys? Let's do eggshell planet. Let's do this. All right. I got a couple more things I want to show you guys. Just a couple more things, then I'll give you guys the rest of the class. Okay. All right. So gravity field, circa a planet. So if you're on the surface of the planet, you feel some gravity field. Here, I have gravity field as a function of distance from the center. You guys see that? So the zero could be at the core. You guys got that? So all of us have spent our entire lives at the surface of a planet, Earth. Right? So I'll call that fixed R, capital R. Right? So we all experience this surface level G. You guys got 9.8 meters per second squared. Right? Because as you take off in a rocket, get further, further away from the planet, does the gravity field get weaker, weaker, weaker? And it tapers off 1 over the distance squared. So if you're twice as far out, like if you're on top of a tower that was as tall as Earth's radius, right, then you would experience how much of the gravity field compared to the surface? 1/4, 1/4, and you have 1/4 of your weight. If this guy weighs 100 pounds, I bet this guy only weighs 25 pounds, right? Okay. Right. Then how about if you go inside the Earth? Suppose you tunnel all the way to the center. Let's ignore that's all molten. But besides that, say if it's all solid all through. Get to the very center. What's your weight right at the center? Zero. Because every grain of sand pulls you a different way. It all cancels out. So that's this point here, 0, 0. 0 from the center. Got 0 gravity. Okay. Oh, now what about this guy digging the spiral staircase all the way down? What if he's halfway to the center? I'm making the claim here that he would have half his weight. You see it? Now this is one of those proportional type questions like we were just looking at for escape speed. Right. Now, I want to prove that to you guys real fast. So this will be the last thing. Right. Now, to prove that, I need to introduce that with a different idea first, which is, and this is going to connect back in and be able to prove eggshell planet. Suppose you're tripping around the galaxy, seeing all these crazy planets. You come across this one planet. You're walking around the surface saying, I think there's something weird about this. Right? So you dig a tunnel and look through like, whoa, this planet is completely hollow. It's a giant eggshell. Something really weird. Now, you can walk around on the outside. Right, the collective mass of this is like at center mass could be still center, it's still pulling you down. That's all fine and good. Once you step inside this eggshell, the gravity completely cancels out. Right? And I want to convince you guys that's the case. So I could pick a random point, like right here. Let's say there's some distance to the surface. I'll call it R over here, and there's 3 times the distance over here, like 3R. So R versus 3R. You guys that? Now, if you make you guys see whatever's pulling up and pulling down is going to cancel, obviously. So up and down cancels. But what about right and left? If you can prove right and left cancel, then that could confirm that gravity-free interior. Right? So suppose you make like this cone wedge. You say, like, how much mass is this over here? Okay, so that's the mass that's pulling you to the right, right? And then what about to the left? Well, see, it's 3 times further to the left, but this could be like an area. Think of that, or maybe it's like 1 foot thick. But guess it would be 9 times the area. And if it's the same thickness, therefore it'd be 9 times the mass. Right, so here's what's pulling you to the left. GMM on R squared, but it's 9M and 3R. And here's what's pulling to the right, just GMM on R squared. Okay. Do you guys see that the over 3 squared could give you a 9 on the bottom, and this 9 could cancel? So it's exactly the same force both ways. Okay, is that right? Right. Now, what does that have to do with tunneling into a solid planet? Because if you're like halfway down, everything above you, you could think like 1,000 different eggshell layers, and each one of them cancels out. So it's as if you're standing on a tiny planet with only the ground beneath you, all the way down to the core, right? Yes, I do. Right. And if you get that, I could say, well, let's do gravity field, because that's what I got on that. Well, on this graph right here, I got gravity field. Right. Guys, what's an expression for universal gravity field as a fraction? How's it go? Yeah, GM on R squared, or something like that, right? Maybe I'll do a variable R, like you're tunneling down. Remember, everything above you in elevation cancels out because it's just a series of eggshells. So we got that, right? Right. And I want to prove that on this graph, as you tunnel down, this is going to be a straight line, okay? You guys see what I'm trying to prove, right? Hey, I wonder what the slope of this line is even. We can find out the slope of that line too. All right, let's figure that out. So We got here. So G equals, well, instead of mass, isn't mass just density times volume? And okay, so here's density. And isn't volume for a sphere 4/3 pi r cubed? Like that? Isn't that also true? Right? It's approximately a sphere. I'm going to put, instead of mass, I'm going to do 4/3 pi r cubed. This is all divided by r squared. Hey, what cancels? Two of the r's, right? So gravity field equals universal gravity constant. I got a 4/3 pi, right? This is all times r, right? Right. So this is, remember, tunneling down inside the planet. Just what's the ground beneath you? It looks like this, and everything above you cancels out. It's a series of eggshells, right? This is the equation of this line right here. Here's gravity field as a function of distance from the center of the planet, right? This is a linear relationship. You guys see gravity field is just plain proportional to your distance from the center, right? And here is the slope, right? Capital G, that's a constant. 4/3, that's a constant. Pi, that's a constant. So whatever number that is, that's the slope of that line. Okay, like I said. All right. Okay. So yeah, so I got in all the demos I want to do. So go ahead, give you guys the rest of the class. Oh, good, we got a solid 20 something minutes in here. 20 minutes. All right, so go ahead, do as many as you can here. Guys, when do these puzzles due? Friday. Yeah, so puzzles due Friday. I'll walk around, help you guys with any questions that you have.